Next talk will be about corecursion. In particular, it will be about a framework for defining corecursive functions in ROC. The paper is by Jaewoo Kim, Yeonwoo Nam, and Chung-Kil, and the talk will be given by Jaewoo. Please.
Present Coco for corecursion with compositional heterogeneous productivity, which is joint work with Yeonwoo Nam and Professor Chung-Kil. I have structured this talk into two main parts. First, I'll explain how corecursive definitions work and the challenges they introduce. Then, I'll present our key approach to resolving these challenges. We will start by introducing coinductive types in comparison to inductive types. On the left, we have a standard binary tree, which is finite. This is a typical example of an inductive type. On the right, however, we have an infinite binary tree. This is the key difference. While inductive types are for finite data, elements of coinductive types can be possibly infinite. This allows us to use them for modeling infinite structures and behaviors. In this talk, I'll focus on the stream, which is the canonical example of a coinductive type. In ROC, we define it using the coinductive keyword to mathematically represent infinite sequences of integers. This definition gives us the constructor as-cons of type into stream, denoted here by the double colon. For this type, we also have the natural destructors as head of type stream to int and as tail of type stream to stream. To construct elements of a coinductive type, we use corecursive definitions. For example, let's look at zeros, a stream consisting of infinitely many zeros. Its first element is 0, and the remaining tail is, once again, just zeros. Because of this self-similarity, we can define it cyclically. We view this stream as the fixed point of the generating function, lambda self, 0 as-cons self. The cofix operator, colored red, returns the unique fixed point of this generating function, provided that a unique solution exists. Let's expand this definition step by step. If we unfold zeros here and substitute it with 0 as-cons zeros, we get this, and if we unfold zeros here again, we get this, and it produces element 0. The stream is uniquely determined, so we say it is well-defined. However, not every cyclic definition is well-defined. Consider IL defined as the fixed point of lambda self. Expanding this definition simply yields IL again and nothing more. Since it fails to produce elements, the stream is not uniquely determined. Therefore, we say this is ill-defined. However, there is a limitation in ROC's handling of corecursive definition. Consider growing, defined as the fixed point of lambda self, 0 as-cons as map as self. Here, as map as simply increments every element of a stream by 1, as in the example on the right. Let's expand this definition step by step. If we unfold growing here, substitute it with 0 as-cons as map as growing, and simplify it a bit, and unfold growing here again, we see it produces elements without issue. Conceptually, this should be well-defined. However, ROC rejects this definition since the ROC checker does not know that SMAP S is safe here, that is, it preserves productiveness. ROC is being conservative. After all, if SMAP were an arbitrary function, the definition would not be guaranteed to be well-defined. Now, let's look at existing solutions to this problem. First, there is the contraction method. Here, the user can manually prove the contractivity property of a generating function to guarantee that its fixed point is well defined. However, a limitation of this approach is that it is not compositional, that is, we cannot decompose the property into components and derive the overall property from them. Also, there is the Miko, which achieves a degree of compositionality by introducing the friend concept. In a sense, functions are registered as friends based on their syntax if they produce n elements by consuming n elements. Then, the Amico library can automatically validate corecursive definitions composed of these friend functions when it is guarded by an additional constructor. Let's look at our example growing again. Here, SMAP produces n elements by consuming n elements. In the example on the right, if the input has 2 elements determined, the output of SMAP also has 2 elements determined. Therefore, it can be registered as a friend, and growing can be accepted. However, the compositionality offered by Miko has its limitations. Consider Fib, the Fibonacci string, defined as the fixed point of lambda self, 0 s-cons, 1 s-cons, addition of self and s-tail self. Here, the plus sign notation is for the element-wise addition of the strings. Ideally, we want to decompose the function into components such as s-cons, element-wise addition, and s-tail, and prove it is well-defined simply by composing their properties. Nevertheless, s-tail is not a friend. This is because it consumes 1 more element than it produces. Therefore, we cannot verify Fib in this form using the friend concept alone. Our work extends this compositionality further using CHP, Compositional Heterogeneous Productivity, by assigning quantitative productivity values to component functions. This enables greater decomposability and widely applicable automation. Coco is our implementation that uses this theory to automate this process. This brings us to part 2. Now I will explain the key ideas behind CHP and Coco. So, how do we introduce quantitative productivity? Let's start with a naive integer-based approach. First, we assign integer productivity to component functions. For example, s-cons is assigned +1 since it produces n plus elements by consuming n elements. In the example on the right, we see that providing 2 input elements determines 3 output elements. Similarly, s-tail is assigned -1 since it produces n elements by consuming n plus 1 element. In the example on the right, we see that providing 3 input elements determines 2 output elements. And SMAP is assigned 0 since it produces n elements by consuming n elements. In the example on the right, we see that providing 2 input elements determines 2 output elements, the same amount. Next, we sum these values to derive the total productivity of the generating function. If the result is positive, that is greater than or equal to +1, then the fixed point is well defined. Let's look at examples. For zeros, the generating function uses s-cons once, so its productivity is +1, confirming that it is well defined. Conversely, for il, the productivity of the generating function is 0 because there are no components to consider in the counting. So il is ill-defined. For growing, there is 1 s-cons plus 1 and 1 SMAP s, 0, so the total productivity is +1 plus 0 equals to +1, identifying it as well-defined. However, this naive mechanism falls short in some cases. Consider S1 defined as the fixed point of lambda self, asset self s-cons, 1 s-cons, s-tail self. There are 2 S-cons and 1 S-tail, so if we calculate the productivity using simple sum, it evaluates to +1 + 1 - 1 equals to +1. Yet, if we expand the definition, unfold S1 here, and simplify it, we hit a dead loop. We get that the head of S1 is set S1, and nothing further happens. It does not produce the first element, so it is actually ill-defined. Intuitively, S consumes data in some way, so it needs to be taken into account in productivity counting. But there is a problem. S returns an integer, not a string. So the meaning of productivity for S is unclear. There are no elements to produce or consume for integers. Still, to proceed, an ad hoc fix for this is to assign -1 to S, reducing the total productivity to -1 + 1 + 1 - 1 equals to 0. Now it correctly reflects that S1 is ill-defined. But this fix still has a problem. Let's apply this ad hoc assumption to another example. S2, the fixed point of lambda self, 0 S-cons, SS self S-cons, S-tail self. There are 2 S-cons, 1 S-head, and 1 S-tail, so the productivity sums to +1 - 1 + 1 - 1 equals to 0. This suggests that S2 is ill-defined. Nonetheless, when we expand the definition, unfold S2 and substitute it with 0 S-cons S-head S2, S-cons S-tail S2, and simplify it a bit, it successfully produces a stream of zeros. So this is actually well-defined. This shows that we cannot simply assign productivity -1 to S-head. Then, what is the correct productivity for S-head? CHP solves this problem by generalizing the notion of integer productivity to handle heterogeneous type. Let's look at how this works in detail. In CHP theory, to handle various domain and codomain types, we assign a specific level set and a corresponding equality up to relation to each type. For a stream, the natural level set is net. 2 streams are equal up to n if the first n elements coincide. For example, any 2 streams x and y are equal up to 0. Also, 42 S-cons x and 42 S-cons y share the first element 42, so they are equal up to 1. For int, we use a different level set, bool. 2 integers are equal up to true if they are identical, and any 2 integers are equal up to false. For example, 42 and 42 are equal up to true, but 42 and 37 are only equal up to false. The level set of int times stream follows naturally from this. It is the product of the 2 level sets. 2 pairs are equal up to a level L1, L2 if the first elements are equal up to L1 and the second elements are equal up to L2. Therefore, 42 and 0 S-cons x and 42 and 0 S-cons y are equal up to true and 1. Crucially, Coco selects the level set for these types and other types automatically. Now, let's look at the formal definition of productivity. Consider a function f from type C to D. The productivity P is defined as a relation on the level set of these types, level of C and level of D. We say that f is P productive, or f has productivity P, if it satisfies the following condition. For any output level L out, if 2 inputs C1 and C2 are equal up to all input levels L in related to L out by P, then the outputs f of C1 and f of C2 equal up to L out. With this definition established, let's apply it to our standard constructor and destructors. For STL to produce n elements, we need n plus 1 elements from the input, so the productivity relation requires n in to be equal to n out plus 1. We also include the condition n out is greater than 0 in the productivity, since no input elements are needed to determine 0 elements in the output. In the example on the right, we see that when 2 input streams are equal up to 2, 2 output streams are equal up to 1, which matches with the productivity. For ASCIIs to produce an element, we need a valid integer for the head and a tail of length n minus 1, which is why there are two conditions, b in equals true and n in plus 1 equals n out. In the example on the right, we see that when 2 integers are equal up to true and 2 streams are equal up to 1 in the input, 2 output streams are equal up to 2. This matches with the productivity. For asset to produce an integer, we need at least one element, so the condition has n in equal to 1. We also include the condition b out is true in the productivity, since the equality up to false trivially holds. In the example on the right, we see that when 2 input streams are equal up to 1, the output integer is equal up to true. Coco generates these productivities automatically. Furthermore, these productivities are compositional. We establish this via composition lemmas for standard combinators, such as the constant function, sequential composition, and pairing combinators shown here. Each lemma shows exactly how to compose the productivities of the component functions. For the constant function, the corresponding productivity is just the empty relation, or false. For sequential composition, it corresponds to relation composition, and for the pairing, it corresponds to a form of disjunction. Similar lemmas exist for other standard combinators. Currently, to use these compositional lemmas in Coco, the function must be provided in combinator form using the combinators shown on the previous slide. Note that if we unfold these combinators, we recover the original definitions. Thus, they are definitionally equal in this case. Automating this translation to combinator form is a topic for future work. Now, let's see how productivities are composed in action using the example S2. We will show the productivities of intermediate functions step by step. Note that each function and its corresponding productivity are color-coded to match. We start by pairing SAT and STL using the pair lemma to obtain the intermediate productivity. The disjunction that was in the lemma appears here. Next, we compose this result with ASCIIs using the sequential composition lemma. Now, relation composition is used. We see this in the form of the existential quantifier, exist N1, B1, and the conjunction. After that, we pair this result with const 0, using the constant function lemma and the pair lemma. We see another disjunction, including the occurrence of false. Finally, we compose this result with the outer ASCIIs using the sequential composition lemma again. We see another relation composition. This gives us the total productivity of the generating function of S2. Finally, we compare our composed productivity against a reference productivity, one that ensures progress shown here in pink. This loosely corresponds to the +1 requirement in our previous naive approach. If the derived productivity is included in this reference productivity, the fixed point is guaranteed to be well-defined. The inclusion condition is expressed here by the right arrows implications. For S2, this condition is satisfied, so the fixed point is well defined. Coco generally automates these checks using a specialized tactic, primarily based on the NIA solver. Let's do this one more time with S1. Here is the derived productivity from the composition lemmas, and here is the condition. For S1, this is not satisfied. We can find a counterexample when n0 equals 1 and n3 equals 1. This matches the fact that the fixed point is ill-defined. In our paper, we provide the full details on how to assign productivity to functions of arbitrary types. For example, even a function from the sum of string and binary tree to the product of string and integer. Furthermore, we present composition lemmas for a wider range of combinators, including function product, copair, and coproduct. The one other important concept I haven't mentioned yet is second-order productivity. The question might arise, how does Coco know that S map S is zero productive? While it is possible to prove this manually, our second-order productivity is the key to doing it automatically. We won't go into detail about the definition of second-order productivity here, but it is compositional, just like the first-order productivity. From this, we can derive the productivities of more complex and interesting examples using our theory, including ones for mutual corecursion. These are in the paper and in the artifact. In conclusion, CHP enables the compositional calculation of productivity for heterogeneous component functions. Complementing this theory, Coco is our rock library implementation that provides high automation for this process. We have several directions for future work. Here we highlight some of them. First, compared to tools like Amico, Coco currently requires more boilerplate code, and we aim to improve our engineering of low-level automation to increase usability for the general user. Also, while mixed recursion corecursion inherently requires a kind of termination proof, there is room for improvement in the automation support for this in Coco. Additionally, we plan to port our library to Lean, another well-known proof assistant. Thank you for listening.
Thank you. We have time for maybe one or two quick questions.
Thanks for the talk. I think this work is quite kind of related or comparable to guarded type theory, which uses step indexing or cryptic key semantics to deal with like semantic notion of productivity, which is actually contractivity in their theory. So I think the main difference is the index is like usually natural number or globally fixed in their work, but in your work it's local. But in guarded type theory, it has a kind of advantage that like it can handle like higher order data types, like function can be under the later modality like that. So how do you think like guarded type theory and your work can be combined?
Thank you for the question. I think our work and the guarded type theory took different approaches. We do not have to change the types in our theory, annotated with some numbers. And as far as I know, guarded type theory requires some numbers as in size type or some modalities. And we do not need that, and this information is included in the productivity. And also about the function, our theory and Coco can also deal with functions. A function is just another type combinators that can be handled by Coco. And also there is the theory of second-order productivity, which also gives the productivity of the fixed point of the generating function, not just the existence of the generating function's fixed point. So does this answer your question?
I wanted to ask about like non-monotone data types, like because function is covariant, contravariant in the argument. But maybe we can discuss offline. So thank you.
Okay, thank you.
I fear we have to move on. Let's thank the speaker again.